What was that? That's not me, for sure. So I am Kiro, co-founder and CTO of Meilisearch. Maybe you know about that. You have probably already seen me on the internet. I am a Rust advocate. I started with Rust in Rust 1.0 when it was crashing, not compiling, very hard to understand what lifetimes were, and stuff like that. And you can find me on the internet through the name of Kiro Maps, and you've probably already seen my profile pic somewhere. So today, we'll talk about AI agents, how to build RAG, automation with AI, and how to code with AI. Okay, you broke my joke, but like, no, it's a joke. We'll not talk about that for sure. We'll talk about Meilisearch, and we'll see that today. So I will introduce Meilisearch, what it is. Probably already know that, maybe. Why Rust was the right choice, and how we scaled over years, and some thought about AI still. So Meilisearch is a search engine, not a Google-like search engine, or Bing, or DuckDuckGo, whatever you want, whatever you use. It's more like an Elasticsearch-like search engine, Algolia, QuickWit, TanTV, you know, all this kind of stuff, all based on single key value store and stuff like that. We'll talk about that later. It's highly performant. It like answers in probably locally with a small data set in less than a millisecond. When you start to increase the data set's size, it probably take 12 milliseconds, 20 milliseconds max. And over network, on our cloud, it's probably around 50 milliseconds. It's relevant out of the box, so it supports typo tolerancy, prefix search, and grams and stuff like that. And it's very, very simple to use. That's kind of an issue too. How it all began. So I started working at 42 in 2013, in Paris. 42, the 42 school, if you want, is a French free code school. And I met Quentin and Thomas there around in 2014, maybe. And then we met again at Veepee, which is one of the largest e-commerce company in France. And Quentin, Thomas, and I, so the three co-founders, were in a lab, so the Veepee lab. And we we were working on different projects to improve the quality of the company, like improve processes, simplify stuff, etc. A lot of projects. And at some point, I was hired by Veepee and was no longer working in this lab. I was a bit sad. But like, Quentin was working in this lab still, and he worked in a team who wanted to revamp the search engine of Veepee so that people could search for red dress and not find wine. So I was a bit like not happy about the fact that they decided to use Go to build this search engine. So on my free time, I decided to write it in Rust from scratch. My engine was, the engine I worked on at first was much more performant than the Go one. As you may guess, there were like a lot of GC passes that you can see on the performances of the searches. So some searches were like 10 times slower than others. So we decided to go with Rust. It's much more performant, and the result is here. Meilisearch is in Rust, and it's a company, a whole company. Then, so we had a search engine that we needed to sell, and we were working from 42 school because like we didn't have any offices and stuff like that. We were working and living out of our pockets. So at some point, we were lucky. On a weekend, Louis Vuitton decided to organize a hackathon at 42 school. Very lucky. And we decided to participate, and we won the hackathon against Algolia, which is like a licorn, a unicorn, and Elasticsearch. Algolia is also French, by the way. Yeah, French loves to work on search engines, it seems, like TanTV. And we won the hackathon, And at this point, we had a contract with Louis Vuitton in 2019, where we signed some papers to say that, yes, Meilisearch will still be open source, and we will just install the engine on the Louis Vuitton infrastructure and continue to work from there. At some point, we raised some funds, in 2020, early 2020, and we started hiring people, etc., because we decided that we didn't want to work for only one company. It was like not very good, plans. So we lived happily ever after. No, it was very hard. We had a lot of challenges. We were early adopters of Rust, and you may know at the beginning, Rust was like a very, very good language. It still is a very good language, but like we had a lot of issues, and especially in terms of libraries, available libraries in crates.io or anywhere else. So we had like a lot of missing libraries, like for example, replicating to replicate the content of databases. When we were at Louis Vuitton, I designed, and I'm probably not proud of that, but I designed a Redis protocol-based system to do event sourcing, so like gather all the requests that were going to one Meilisearch, to put them in an event store, and the three or all other Meilisearch instances were receiving the messages and indexing and gathering the content. It was ugly as heck. It was breaking everywhere. It was very hard to maintain, not performant enough. That was probably the first time I was doing network stuff. So yeah, very not proud of that. But it was a solution. There was no very good Raft or Paxos libraries, and it's only this year, right now, in 25, that we started working on sharding the content of sharding and replicating the content of Meilisearch over multiple machines. And we have one of our largest customers working with that in production, and it still works. I hope so. But like, yeah. It was a subject since the beginning, replicating content on multiple instances so that when one Meilisearch instance crashes, we have still other Meilisearch instances to work with and to answer requests, search requests. Another main point, because I'm more in this area, like I'm more like in the key value store domain than the network domain, but like there were no very good key value store or key value store wrappers. We started working with RocksDB, RocksDB wrapper maintained by Tyler Neely, or Space Jam, that you can see the first white picture under the contributors. Is a maintainer also of Sled, but I will talk about that later. And the wrapper of RocksDB was like segfaulting a lot. There were a lot of performance issues, but it's not the wrapper problem. It's really RocksDB that was doing a lot of compactions, consuming too much RAM. It was crashing Meilisearch, a lot of stuff, ugly stuff. So I started working on Sled itself, and that's funny because I'm still the fourth contributor, even though it was like probably 6 or 7 years ago. Okay, that's a joke. So yeah, I started working on Sled I did a couple of pull requests, and we also donated a bit of money to Sled so that they can work on some like performance issues we were having when we tried to integrate it into Meilisearch. And then after like probably 1, 2, or 3 months, I don't know, we discovered LMDB. LMDB is a memory mapped, lightning fast, at least that's the description, in C key value store. So it writes everything in a single file. All your key values are in a single file, and it's managed by pages and stuff like that, very complex stuff, all in C. So I built one of the most popular Rust LMDB wrapper right now. It's not one of, it's the most popular Rust wrapper right now, because Mozilla, which was using LMDB in Firefox at some point, started archiving their repositories and didn't want to maintain their wrapper. And anyway, it was not fitting correctly inside Meilisearch, so I designed something else. We had other issues, other problems. So one problem that we still have right now is about like the compile times, and you may know what I'm talking about. But like Rust Analyzer, it's not the compile times, but like especially for Rust Analyzer also, we have issues when we try to autocomplete or like just complete what we are typing, like Rust function and stuff like that. It takes a long time to autocomplete stuff, and advice is welcome. We tried like to split the Meilisearch source code into multiple crates. We already tried that, but we still have one large library that depends on one another large library, and it's just not helping much. We also tried to move the tests out in different files so that we don't compile. I mean, Rust do not try to read the tests, even though, because it will not need them. Don't put tests at the end of your files. Put them in another module. It's better. And one thing that, like, one very big problem that we also always had with Meilisearch was the time Meilisearch takes to index documents. So what it means, when you send documents to Meilisearch to index them, Meilisearch will just put them in a task queue to manage them later, not live because it takes time. So we don't want to block an HTTP request or whatever. We put them in a queue. We answer you like immediately. And then Meilisearch decides to batch multiple tasks. So for example, batches of 300 documents or stuff like that, and then index them in bulk. We tried multiple stuff, like for example, at some point in one of the Meilisearch versions, I don't remember which one, we have a lot of versions, but like there is, at one point we were like soft deleting documents. So instead of deleting documents IDs from documents that you remove from the inverted indexes, where you have the word corresponding to all the documents that contain this word, we were just marking them with tombstones somewhere in another database. And when you were doing searches, it was like finding all the documents, so the deleted documents and non-deleted documents, and cleaning that up afterward. So all search requests were doing more work than could have been done. We removed that quite quickly, because it was like doing like large garbage collection passes to remove the document in one go. It was taking time. And I wrote a blog post that you can see on the right about how the techniques that you can use to use LMDBs the right way to multi-thread stuff, because when you have a key value store that is like managing all the memory and stuff like that, it doesn't allow you to do a bunch of stuff. But like, because I probably was young when using LMDB, when I used LMDB, I forgot that you can use like multiple read transactions to read the content on disk and read like the inverted indexes and stuff like that. So I wrote a whole blog post about that, so you can understand and use all those tricks. I will talk about one just after that. And we also like design, but it's a next subject, a vector store. I don't know if anyone here knows what is a vector store or embedding store. Can you raise your hand? Yeah? Okay, not much. Okay, so when you are doing, we'll talk about that a bit later, but just so I know. I rewrote the engine probably 4 times, just because like, when you write the engine the first time, it's badly designed. When you write it second time, it's badly designed again. And there are a lot of problems that you see in your code, and you are like, okay, I should have written this way, it's this way, etc. And also, as a side note, I am the maintainer, the full-time maintainer of the Roaring Bitmaps crate, Roaring RS crate. It's a full Rust Roaring Bitmap crate that we use into Meilisearch. It's designed by Daniel Lemire, and it's Roaring Bitmaps are like sets of numbers that you can do operations, fast, quick operations on. Like for example, like unions, symmetric differences, intersections. And we use that in Meilisearch everywhere. And we are maintaining the crate. Then came AI. So AI is, it's a big word, but like we will talk specifically about semantic search. So semantic search, like Meilisearch was designed to do quick and very relevant keyword search requests. So it is capable of extracting the keyword from your query and searching into the key value store and the inverted indexes to fetch the best documents. It is capable of splitting your word to generate like n-grams and find the best n-gram in the key value store, etc. A lot of stuff to help you find your documents. But the semantic search is another aspect of search. It's more designed to search for stuff that you don't yet know. So you don't know the keyword to search for. It's more designed to help you like find stuff based on concepts. The basic stuff is that you ask an embedder. So it's something that generates embeddings. And embeddings is basically just an array of floats. So like a point in a n-dimensional space. And this vector is like a representation of the text you gave it. And it decides to put it like close to the olives or to the pizza. And when you are doing a query, the embedder will do the same. It takes your query, generate a vector from that, and then you have tools to do like NN search, so approximate nearest neighbor search, that fetches the closest documents or points to your query vector. That's based, everything is just based on semantic and understanding of your query. And we talk a bit about that. So when AI came, semantic search was something that we wanted to implement in Meilisearch. And we did something very cool that we implemented like hybrid search. So when you type your query in Meilisearch and you want hybrid search, the engine will do a query on the keyword with your keywords first, and then we'll do an ANN search, so approximate nearest neighbor search, and we will merge the best results and only output the 20 top results, so that you have the best of both worlds. We compute scores on that, etc. When we first implemented our vector store, we started with instant distance, which is built by DJC, which is working on Rust, I think, a Rust compiler and other libraries. The main issue of that is that it's full RAM. So every vector you put in this store, it is put in memory. It's not necessarily an issue when you don't have a lot of vectors, which was okay, but it was not scaling well. And one of the reasons why is that because Meilisearch is using LMDB as a key value store. LMDB is transactional. So every time you write something, you want to write something in the key value store, you first need to ask for write transaction. Then you do all your changes, and then you decide to either abort the transaction or commit the transaction. Everything that is not yet committed cannot be read by such requests. In fact, read transaction will not see the content of your writes if you don't commit. So the thing is that if we want the freshest data to serve to your customers or to the clients, you must read the content from the database, and therefore we needed to serialize this large data structure, this large SNSW, on the disk in LMDB, and every single search request was deserializing the data structure in memory, reading it, and dropping it just after. It was absolutely not efficient. It was like crashing everywhere. Even though Meilisearch boots in like probably less than 100 milliseconds, it was not efficient because like search requests were just dropped. So someone asking for something and the server never answering. That's not a good thing. So we looked on the internet and we tried to find a good vector store, memory mapped vector store, because like we wanted to store everything in LMDB so that the key value store was used for the HNSW or the data structure we decided to use to search for vectors. And in a week, in fact, we found something and we built something, we rebuilt Spotify Hanoi, which is like vector store designed by Spotify, sorry. And it was not based on LMDB, it was based on raw files, so every time you wanted to add a new vector, you had to rewrite everything from scratch. So it was not designed for us, but we decided to take it, look at how it works and how it writes entries in the file, and just put it on top of LMDB. It took only a week to do that. And at the end, we also had more features, so like filtering, and etc. We are quite proud of us. I wrote a blog post also about that, that I will just open after. And it's based on random projection, but we will talk about that just after. It's not an HNSW, it's something different. We still had a lot of issues and pain to scale, and we lost big customers due to that because we were not able to scale. I will show a bit of Rust because I think you would like to see a bit of Rust. But like, as I was telling just before, does it fit? Yes. I was telling just before, like LMDB lets you read in parallel everything that you have committed. But there is an issue. When you write something into a write transaction, it's not visible to the outside world, to the outside read transactions. It's visible by you. You can read what you write, but you can only do that from a single thread. So you cannot like have multiple readers on the content you have not committed yet. So we designed some tricks, and one of them is this one. It's not very complex, in fact. It's unsafe. Yeah, there is an unsafe somewhere. I don't know exactly where, probably there. Yeah, close to the slice. What we do is that we iterate on all the items. So the items represent the vectors. All the vectors, so the embeddings I was talking about before, are all the same length. They are all the same size. So we just have to store the length once in the constant length field of this struct. And we iterate over all the items, store the items in a big roaring bitmaps, as I was saying before. It's a list of numbers, if you want. And we store in a vec just below, in the offsets, the pointer in the memory map of the vector itself. So yes, it's unsafe. And then we make sure that the lifetime of the transaction that you can see, it's t, is never like outlived. So it means that the pointers are constrained by the lifetime t, which is the lifetime of the transaction. So while the structure is owned, you cannot drop the transaction, and therefore the pointers point to valid data. And at the end, on the get side, on the get function, you can see that we just get the constant length. If it's not set, it means that we haven't like found anything in the database, so you can return no. We don't see any vector with this ID. But on the other hand, if you find something, if you have a constant length, you will just get the rank. So it means like the position in the large list of numbers where it is it the fourth one, the fifth one, etc. You get it, and you get the offset, and you generate a slice, a fake, not a fake slice, but a reconstructed slice from that, and you can output that. And at the very bottom of this code example, you can see that it's again unsafe, but I am telling the compiler that yes, this structure can be used from multiple threads. It's safe because the data is valid until I dropped the transaction. Okay, and I can show you the stuff. When you are reading from the disk, there is a main thing to look at on this hashtop screenshot. But like when you try to ingest 25 million vectors of the dimension I specified, you can see that the CPUs, even though it's multi-threaded, are just not doing anything. Like they are blocked. And you can see something very interesting. You can see the memory that goes very yellow, too yellow for me. And the swap is just overused, like it's full. And in fact, you can also see on the large yellow line that we are doing a lot of disk reads. You can see that there is 1.6 gigabytes of disk reads. That's too much. And in fact, what we were seeing is that even though LMDB is memory mapped, it's memory mapped. So if you don't have enough memory to put your pages in the page cache, you will just read the disk, and that's it. That doesn't make sense. It's not useful at all. And I verified what I was saying by this new screenshot that exposed that with 15.6 million documents, vectors, we can see that Meilisearch, it's not exactly Meilisearch, but Meilisearch is doing a good job. Every CPU is at 100%, and there is not a single disk read. So we are reading everything from the page cache. Everything is full. Everything is working as expected. And after this long talk, we can see numbers because it's interesting. Hanoi is the Spotify Hanoi library. And Arroy, yes, best name, Arroy is the library that we rewrote in Rust and based on LMDB. And one main difference is that we are faster. And also at the end, you can see that Hanoi is not capable of indexing more than 15.6 million documents. We are capable of indexing 36% more vectors than Hanoi. And you will tell me, yeah, but you just rewrote the library, or is it possible? In fact, the main difference is that when you write into LMDB, LMDB doesn't write into the memory map buffer itself, so in memory. It is writing directly to disk, skipping the page cache. And Hanoi, from Spotify, is in fact writing the new vectors and graphs and stuff in the memory mapped, mutable memory map of the file itself. And in fact, evicting too many pages from cache just to write something that it will never read. I mean, read later, but not in the process of indexing stuff. Which means that by directly writing to disk, you skip the page cache and you have just more performances. But like, it was very complex. We lost a lot of customers, not a lot, but some customers due to these performance issues. It worked well for 2 years. And then came the power of open source, and I met Nate. And today you will have the great pleasure to meet him again also. Please welcome Nate.
Hello, everyone. As hinted by Kiro, I'm Nate. There's a lot of you out there, which is pretty crazy for me. So I'm going to try not to make a fool of myself. As this slide says, I'm Canadian. It's probably the most important thing about me. I work at Mistral AI. I don't know if I'm legally allowed to say that or not, because they didn't pay for me to be here, and they also did not support the project. And I do Rust sometimes. I've been a Rust station now for about 2 years, which makes me quite young compared to a lot of you guys, and Kiro notably. And yeah, I'm just here to share Hanoi, which started as a passion project that ended up having real use cases in Meilisearch. So a bit of context, my relationship with Meilisearch as a company was not always smooth. A few months ago, I was working at a different company, and we started using Meilisearch internally. It was my job to kind of integrate that. And I discovered it was written in Rust. I obviously fanboyed a bit and crept all of their GitHub repos. I stumbled across Arroy, and there was only 2 contributors on it. Kira is showing my first ever PR. This is my first ever open source contribution, actually. And it's still open, so that's great. I'm sorry, it's in red also. I'm a little colorblind, so I've switched the settings. That might perturb some of you guys. So not being dissuaded, I was like, okay, whatever. I'll work on other stuff on the side. I want to get noticed by these guys. I want to do some, it's cool just to be a part of something that big. So I made a contribution on Meilisearch, the engine. And directly, I was accused of being an LLM, which didn't feel great. And it's actually a miracle we're still here today. I just kept at it. I kept pushing PRs until, I guess, either out of them being annoyed with me, or maybe I did something good, Kira reached out to me, and I dev'd a few features for Arroy. And it was during that time that I just, like, I'm a math guy, I'm a math and stats person, and I'm sure like many of you, I missed the academia a little bit as I started working in the real world. So I started just exploring some research papers and reading about graph-based vector databases and working on this in my free time. So before I discuss Hanoi, the name also is absurd. I think, a little aside, Hanoi from Spotify, they just took ANN from approximate nearest neighbors, and then the word Hanoi kind of looks like it. Arroy is just because it's in Rust, and Hanoi, I was like, okay, if I throw an H in front, it's kind of like Hanoi, and I can make a cool logo out of it. So I don't know if that was coherent at all, but there's the context. So the way Arroy works is it's based on locality-sensitive hashing, which essentially means 2 points that are close in space will get hashed to the same value, and points that are far apart will get hashed to different values with some probability. This is probably one of the only cases in CS where hash collisions are actually useful. Yeah, so as you can see there, I just showed it on the graph. In Arroy, when I say a hash, it's really just a vector. So you generate a vector that splits your points in half, ideally, and the hash is just the dot product, so it gives you a scalar out. The drawbacks with this kind of approach, however, are that you're generating random trees, right? So you start with a cloud, you split it in half, and then you split the subsections, and you keep doing that iteratively until you get a search tree. Arroy is a collection of these trees. It's an ensemble of trees, but each hash is itself a vector, which takes up something like 4 kilobytes or more, right? So it's quite large, especially if you're generating, like you guys can do the math. It's like log 2 of the number of elements, 2 to that minus 1. So it takes up a lot of space, and that's not really an issue because storage is cheap these days. One of what Kira was hinting at before, like the long build times, that comes from the fact that to generate the hash, that vector, you're randomly sampling tons of points, you average them, and that gives you a centroid, and then you just turn that into a kind of a separating plane. That access pattern on the data is not at all deterministic. It's quite random, and a lot of these builds will experience thrashing when the data set gets too large, which slows down the execution a ton. Another interesting thing is that there's a trade-off in these trees with respect to the height and that on-disk size, right? So to avoid exploding your disk usage, they group together a few vectors in each leaf of the tree, which means that when you're doing a nearest neighbor search, you hit a leaf and you have to search over every element in that leaf. So for instance, I don't know, if you're trying to find 10 elements and there's like 1,000 in the leaf, you're doing 100 times the amount of work you actually need to. The last point there, I don't know if it's fully valid. It's a little complicated to rebalance these trees recursively, but maybe that's just a skill issue on my end. Here's a little screenshot. This is an open issue on Arroy from a contributor, Tamo, at Meilisearch, or an employee, former employee. I don't know if you guys can see, but like 75 or 80% of the time there is spent just page faulting. And this is for a build on, I think, like 1 million or more vectors. So that's pretty concerning. So Hanoi, again, it's just an HNSW. Can I get a show of hands for, I know we asked earlier if you guys know what embeddings are. Do you know what a hierarchical navigable small world is? I'm seeing like 2 hands over there, 3 hands. I'll give a brief overview in a second, but essentially think of it as a data structure that's based on graphs. So Hanoi is a key value backed HNSW built using HEAD and LMDB. We use a lot of the same tricks as Arroy because there's some pretty clever ones there, like the parallelization using pointers, which Kira was talking about. It's inspired by a project from Facebook called Face, which is pretty popular. It's also, I borrowed some ideas from DiskANN, which is a paper from Microsoft. And there's a crate out there that I looked at a little bit for the implementation. There's also some Python bindings if you guys want with PyO3. So yeah, there's a little snippet of the code. I don't know if anybody's ever going to watch this in the future on YouTube, but feel free to pause here and check it out. We can move on to the next one. So why was Hanoi needed, essentially, and what are some requirements, right? So as a KV-backed vector database, we wanted to satisfy a few criteria. The first one is it should be able to serve billion-point data sets from a single machine. I don't know, Kiro, today what we're at on Meilisearch.
Yeah, the largest data set is probably around 1/4 of a billion documents. And we also, thanks to Hanoi, reduce the latency of indexation for one customer from 1 month to 6 seconds. So yes, there is a big difference. Yeah.
That was unintentional too. I didn't set out for those metrics. Another key point is to maintain relevancy even after you incrementally add and remove elements from this thing. So as your data changes over time, you don't want to re-trigger a full indexing of the database just to make it searchable again. And the last point is that we're replacing a system that's currently in production. We shouldn't make performance worse across any key metric. That little meme on the side there is because, for reference, a few years ago, all of these things are fully in RAM. And Alibaba was using 16 machines to host like a 2 billion document data set, which is just absurd, I think. Yeah, we can carry on. So HNS-W for beginners. This picture might look scary. Think of it as a data structure that's hierarchical. You have different strata. Up top, it's very sparse, and down below, it's dense. The way search works is that you start in the upper layers, you look at your nearest neighbors, and you move down from the nearest neighbor. And you repeat this until you end up in a dense subspace that's pretty close to the original query. And then there you do exhaustive search. So it's log time, like you'd hope for from something like this. And what's really cool is it's much cheaper to store on disk, right? Because we're representing the links going out from each node as a bitmap, which means it only takes a couple hundred bytes, whereas before we were at something like a couple of kilobytes. The build patterns work well, so you can incrementally insert, remove vectors pretty easily, which makes it well suited for the workloads at Meilisearch, which, as Kira said, are done in batches. And what's neat too is that when you're building this thing, there's actually a lot more reading than writing going on, which means we were able to parallelize it a lot from one of those many concurrent hash maps that are constantly coming out every other week. Specifically, we used Papaya, and then I added a little picture there at the bottom to show that there's like 10 times the amount of reads of the hash map versus we're only updating it 1/10 of the time. So this is probably the most important slide. It shows the performance of this project versus Arroy. So the first graph there is the indexing time. So this data set is 1 million vectors with 768 dimensions. Before, you were looking at something like 40 minutes. This is fully parallelized. I think it was on my MacBook, so it was like 10 cores. So we went from 40 minutes down to 8 minutes. That's a 5x speed up. And then on the search, we also saw similar gains. But again, this is to be expected, right? Because we're not searching over every element in the leaf. Like in Arroy, we're doing 10 times fewer computations. So you'd hope the numbers would look like this. For reference, you're looking at 400 milliseconds for a query on 1 million vectors, and you're now at 40. These numbers, too, are the cold start latencies. So nothing's in your page cache, so you'd expect it to be actually faster after a few searches. This I wanted to show for transparency. So the red curve on the bottom is, so this is, for context, a popular repo called ANN benchmarks from the same guy who actually wrote Hanoi. The curve on the bottom is Hanoi's performance. It's throughput versus its recall performance. The curve in the middle is Hanoi. Hanoi is memory mapped. Hanoi is also memory mapped using LMDB. But this is still with log n lookups. And we are still doing like an order of magnitude better in terms of throughput. And that curve up top is fully in RAM, constant time lookups, HNS-W. So it would be a little suspicious if we were outperforming that. Cool. I think that kind of wraps up my segments. Before I handed it back to Kiro, I wanted to just thank the community because, you know, this would not have been possible without many of the projects that are out there that you guys are working on. And what's neat too is Hanoi is kind of a project for Meilisearch, but also by Meilisearch. Like there's 3 or 4 crates that I'm using that are maintained by Meilisearch devs. And every time Kiro rolls out new features on Heed or roaring bitmaps and stuff, we can directly benefit from that. So thank you guys, and you know, thanks for listening to me for 10 minutes there.
Thank you very much, Nate, for your intervention and your presentation. Just a bit of, so we're on the AI slide, the one I was talking about. I just wanted to apologize again for taking Nate for an LLM, but like what you must know is that it was a period of time, probably like 6 months ago, maybe, when we were like receiving a lot of pull requests from just people trying out Cloud Code or stuff like that, and the pull requests were nonsense. Like it was very complex to know if at the end of the day spending time on external pull requests was worth or not. So I'm sorry again, Nate. Your pull request will probably be merged one day. But like I just wanted to say that you must still be vigilant and responsible when you merge code, because your test CI will probably not see what is being merged, etc. At some point, you may probably remember there was like miners of bitcoins in your CIs. Now you need to approve code. It's probably the same these days, but there is no approve code. I mean, it's already there. So just make sure that you can use. I use AI every day to generate a summary and to summarize stuff, to document, etc. Just make sure that you don't merge bad stuff and don't blame people who are not using LLMs to code. Right. So that's the end of the talk. Thank you for being there. And you can come contribute to Meilisearch if you want. And we also can give you some swag. We have a swag store, swag.meilisearch.com. As we are a company, we also have a cloud offering. You can use the Wheel of Varys code to extend your free trial if you want to test Meilisearch online. And we are doing a launch week, so like a release week, like 1 week, where we announce new features on Monday, 13 October, starting Monday. And you can join and just subscribe through this QR code if you want. Thank you very much for listening.